Hello everybody, it's Mr. Ray here with our next lesson in grade 12 Calculus and Vectors. We are in the Introduction to Vectors unit, and today we're going to look at some of the properties, algebraic properties of vectors, and then just practice applying. This will be a fairly short lesson. And a lot of these properties are going to make common sense. Like you're going to say, well, of course that's true. But these are vectors. So you're going to see things later on that you think might be true but aren't. So you have to kind of make sure you understand the properties and be able to apply them correctly. So we've got our definitions here, vectors and scalars. Remember, a vector has magnitude and direction, where a scalar just has magnitude. And we can multiply a scalar with a vector. We can add and subtract vectors, and then we can combine those operations together. So here we have our properties, and you will have to understand what these different properties names represent. For example, commutative property means when you add two vectors together, it doesn't matter what order you add them. The result is the same, and we've already used this when we did our parallelogram addition of vectors. We could go in either direction and we get to the same resultant. We also have associative property. If we're adding three vectors together, again, it doesn't matter which you add together first. Before you add the third one, it's all the same result. And distributive, once we multiply by a scalar k with two vectors. So you could just add the vectors together and then multiply the result by the scalar k, or you could multiply each of the vectors by k first and then add those two new vectors together. So the distributive property definitely applies to vectors. The zero vector, this is fairly new, well, a little bit different. Just like when you add 0 to a number, you get the same number you started with. Same thing with adding a zero vector to another vector, you just end up with the vector you started with, because the zero vector has no direction, no magnitude, so it's not changing the vector that you're adding to. And then associative law, once we start combining more than one scalar, and you're multiplying a by two scalars, m and n. Again, this is showing that it doesn't matter how we apply this. We could, in this case, multiply vector a by the scalar n, and then multiply the result of that with another scalar, or we could just multiply the two scalars together and then multiply by a. And we could also represent it by this, which is really the same as the second one. Okay, so associative law says that the scalar, if you have to multiply by multiple scalars, the order doesn't matter, and you can multiply the scalars together first, or a scalar with the vector and then with the other scalar. Okay, and then distributive law, we just used this on the previous lesson when we were doing the unit vectors. I believe we did. If you have two scalars again, you can just add the two scalars and then multiply the vector, or you could distribute the two scalars. So you'd have vector m times vector, you'd have m times vector a plus n times vector a. You could do them either direction, either order here, and you get the same result. So let's just practice that. Nothing too earth-shattering here. If we have this expression, we have the scalar 3, and we have this combination of vectors we're adding, and then we're subtracting this combination of vectors. Well, we can just apply these rules up here. So we can do the distributive law of addition. So basically, So we're going to take this scalar 3 and multiply it independently with all three of the other vector combinations. So 3 times 2a would be, we could multiply the 3 and the 2 together and get 6 times vector a. 3 times vector b is plus 3 times vector b. And then same thing with c. We have 3c. Now, for this subtraction, we could, what I would recommend is treating the subtraction like a scalar of -1. So we're basically multiplying each of these scalars by a scalar of -1. So that would be minus vector a, and then minus 3 times vector b, and then -1 times -2c would be plus 2 times vector c. Okay, and now what we can do is just treat these almost like different terms. Like you want to find like terms you can combine. So a like term would be anything with a vector a in. So I could just reorganize these if I wanted to. So 6a minus a vector a, and then I've got my b's plus 3 times vector b minus 3 times vector b, and then plus 3 vector c plus 2 times vector c. And you can see I've got them grouped together so that I can combine each of those mini groups. And you can treat this almost like algebraically, like the vector a is a variable. So like 6x minus x would be 5x. Well, 6a minus 6 times vector a minus vector a is going to be 5 times vector a. 3 times vector b minus 3 times vector b, well, they just cancel each other out. So I don't have to put anything here. And then 3c plus 2c, where c is a vector, that would be 5 times vector c. Okay, so simple as that. You treat it like regular algebra, but don't forget to put the vector symbols on. Okay, one more example. Told you it'd be a short lesson. So this time we have 3 vectors x, y, and z, and they are actual combinations of 3 other vectors I, j, k. This one doesn't have the I in it, but still. Now, you're going to see that these vectors I, j, and k, so I is like, vector I would be equal to kind of the unit vector x. Vector j is going to be the unit vector for y. So I got my hats there. So, and then vector k, that's going to be the unit vector in direction z. So, oops, I had to put a hat on that one. Okay, it doesn't really matter for this exercise, but I'm just kind of warning you, you're going to see these ijk's in the future, and they represent unit vectors in each of those directions, in the x direction, the y direction, and the z. Of course, we haven't talked about 3 directions or 2 directions. Well, we have talked about 2 directions. I believe the next lesson we're going to talk about 3 space. So that third direction will make more sense. Okay, so I'm going to have to create a bit more room for these. So I got vector a x plus vector y. So all I'm going to do is just write what x is equal to. So I've got, I'll put them in brackets to keep it more readable. So I got 3i minus 4j plus k. And then I'm adding y, which is vector j minus 5 times vector k. Okay, so I'm just going to remove the brackets. It doesn't really change anything for this example since I'm adding. It would if I had, a scalar or negative sign in front. So I'll just rewrite them. 3i minus 4j plus k plus j minus 5k. Of course, I'm leaving out the word vector, just make this a little bit shorter. And now I can combine the similar vectors, the vectors that I can combine. So I've only got one of the i's, so that's 3i. I've got a negative 4j and a plus j, so that turns into minus 3j. And the k, I've got plus k minus 5k, so minus 4k. So that would be the resultant of x plus y in terms of the vectors I, j, and k. If we go to the second one, this time we've got x minus y. So I can pretty much copy this first line, just change the add to a subtract. So 3i minus 4j plus k subtract j minus 5k. Okay, so like we did on the previous page, I'm going to remove the brackets, but I'm basically multiplying these two vectors by negative 1, a scalar of negative 1. So I'm going to get 3i minus 4j plus k minus j plus 5k. And now I can combine. So again, I've only got the one I vector. I've got negative 4j minus 1j, so that's minus 5j. And I've got plus k plus 5k, so that's plus 6k. Okay, and then the last one, a little more complicated. So this one we've got x minus 2y plus 3z. So I've got x, definitely put these in brackets. So x is 3i minus 4j plus k with no scalar in the front. This one we do have a scalar, negative 2. So it's negative 2 j minus 5k. And then plus 3 times vector z, which is negative I minus j plus 4k. Okay, so first thing we'll expand using distributive property. So the first one, no change. And now I'm multiplying these two vectors by negative 2, so I get negative 2j plus 10k. And then multiply this set of vectors each by 3. So I get negative 3i, negative 3j, and plus 12k. Okay, so again, there's a lot of different vectors here. So I'm just going to put them all in a different order so I can combine them easier. So I have 3i and a minus 3i. Those are my only i's. Then I've got a minus 4j, a minus 2j, and a minus 3j. That takes care of all the j's. And then I have a plus k, a plus 10k, and a plus 12k. Okay, so now it's easier to combine. I've got those two, I've got those three, and I've got those three. So those two actually cancel each other out. 0, 0i is a 0 vector, so I don't have to write that. Here I got negative 4, negative 2, negative 3, so that's negative 9j. And here I've got lots of k's, 11, 23. Okay, so that would be the result of this algebraic operation. You can see that it makes a lot of sense. It's not any different than working with non-vector algebra. So that's it in terms of examples. Make sure you practice this. I know it seems pretty straightforward, but you'll see some homework questions that are a little bit more advanced. So give them a try. Okay, and next lesson we're going to look at 2-space and 3-space, how those vectors will look. Okay, so have a great day and take care.